to discuss something really cool, and we want to discuss how AI understand our world and from the aspect of disentanglement and compositionality. Yeah, here's our today's agenda, and we're going a standing lineup of speakers, and we're out there exploring the cutting-edge techniques every day. And I think they are ready to sharing their thinking, show off some impressive stuff, and even give us a sneak peek into the what futures of computer vision would be like. So get it started. Okay, think about it. We are at 3PR, right? And we all guys are vision researchers. So here I want to first to unpack how machines can break down complex vision clues into the simple parts and put them together back, and almost like how we humans do it. So it's like teaching AI to understand what it sees. So we first talk about disentanglement and compositionality in computer vision. Okay, a simple introduction of myself. My name is Xinjing, and tenure track assistant professor from New University, Eastern Institute of Technology in Ningbo, short as EIT. Yeah, our university with a high standing point is emerging and aspires to be a world-class international research-oriented university. I'd like to personally invite you to Ningbo to visit and join us building such a world-class research and educational entities. Yeah. Okay, back to our tutorial. And this slide, and we're also familiar with it, it shows the evolution of the AI towards AGI, artificial general intelligence, right? This timeline captures key milestones and events that have shaped the development of AI over the years. And starting from the birth of AI in 1956, I think, with the Dartmouth conference, and we witnessed the emergence of perception neural network. And at the year of 2013, deep learning has achieved the great success in speech and vision recognition, right? And and AlphaGo defeated the human champions, so which marks the entrance into the era of artificial intelligence and deep learning. Yeah. And recently, we observed so many popular works and see the preliminary version of AGI has arrived with the rise of generative AI such as ChatGPT and GPT-4 and Sora and so on. Those developments both all indicate that AI is standing into the AGI era. So what should AGI be like? Based on much evidence collected from many practical requirements, we can define that our nowadays AGI should be a divided system that we can embed in a very complex world like ours, with all its messiness and craziness. And we want this system to learn and build the right kinds of reasoning blocks, like our human, in various development. And we hope use the same system in the different kinds of work. For example, in the world of science, where the concept used in biology are very different from the concept we used in our daily life. But we want the AI system to be intelligent enough, still enough to successfully deal with the new tasks with its own properties and statics, discovering the right way to reason about it, to answer our daily questions like how to cure cancer and so on. So with summary, that we want the AGI system to have such properties. It should have a very strong generalization ability. I mean, it can work in many different scenarios and save common sense based on exploration. For example, when learning, it will not hurt itself and will not hurt the environment. Finally, and also most importantly, the system should be interpretable enough to humans. I mean, we should know AI why make this decision and which factors influence this decision. Okay, so here it comes the question and how to achieve and implement such AGI system. I mean, we can find some inspirations from ourselves. I mean, from our human. Let's see how humans understand and fit this world. For example, how would you describe all the major features of this dog, from his yellow fur, or from his black fur, or from the dark eyes, brown eyes, or the standing ears, dropping ears, or from the size of dog, and so on? If I ask a boy, please put all the features together and let me know which one you choose, and we can he can summarize his what he did from the size, word type, nose color, ear flippies. If he describe a dog following such logic, its size is big, its fur is yellow, its nose black, and has flippy ears, and we will quickly get, oh, yeah, you said it's the middle one, right? But instead, if a boy come up with a list like this, where his description is mixed with size, fur type, nose color all at once, so we would probably be confused about which dog you are describing, right? This is not a good way to represent that space. So we can conclude that a better AI system maybe prefer a compact and disentangled representation space, which is clear and interpretable to reflect data with major features. Maybe we can call them principal components of data. Yeah, which is as opposed to that entangled factors that mess all things together. Okay, then let's talk about the other side. How do humans create new things? We often propose new idea based on the old ideas, so as to create new things. This is because human beings have a propensity to find faults with existing things, and as we always making we're always making improvements to make the things better. Existing ideas evolve and new combinations emerge. Nowadays, we have so many powerful tools to help us create new things, right? As we all know, the most popular AIGC app, Sora, right? Amazing tool to help us create what we want with generative video. We can describe what we want in text, and Sora will output the corresponding generated results. Let's see some examples. Giving some picture units here separately contains dog, sunglass, leg, and the corresponding the textual description. We can generate the corresponding more complex images by combining these visual clues together. Such compositionality is a key nature behind computer vision, which makes human beings common sense. We always create new things, combine many existing simple elements, right, or fundamental concept. Similarly, given the different cases, we should accordingly get the different generated results. So we can see that our human creation ability is also derived from a progressive composition process, which reveals that if we want to achieve AGI, the compositionality should be paid more attention to empower our AI system with a strong generalization ability. All right. Actually, we have already discussed those two important concepts of disentanglement and compositionality just now. Here is the outline of my talk. First is the concept of disentangled representation learning, the full time and short as DRL. In fact, Angel pointed out that as early as 2013, I think, yeah, for AI to understand the world fundamentally, the only way is to identify and disentangle the underlying factors of the observed data. Giving the observed images of 3D scenes for this toy game, the underlying factors are the camera pose, object shape, and so on. With this factor, we can generate and control the image with those disentangled factors independently. For disentanglement, its final goal is learning to extract such representation of factors from the image. Here is a toy example. So we have the ground truth of factors, but for the real world data, typically we need to learn disentangled representation in an unsupervised manner. Like this case, for the real world face data set, the goal of this disentangled task is to learn a representation with each dimension capturing variation of semantic means, such as smile, hair color, gender, and so on. So disentanglement, this concept, is important for both fundamentals and applications. For fundamentals, it can help us help the interpretable reasoning, concept learning, and so on. For applications, it also benefits some such like controllable generation, editing, and domain generalization. For example, if a dog image with disentangled representation, it's possible to control the image according to the text, make the dog happy, make the eyes bigger, while keeping other attributes the same. And disentanglement is also raising a lot of attention, and there are increasing works on it. So this slide highlights three essential aspects of disentanglement for explainable, generalizable, and controllability. Explainability refers to learn semantically meaningful and separate representations aligned with our human-like perceptual factors. And generalizability involves separating task interest in representation from the original entangled input. And the final controllability aims to achieve controllable generation by manipulating the learned disentangled representation in latent space. So these three aspects of disentangle, they're very important and shaping the future of AI, I think, providing the foundation for more advanced and versatile AI system. Here we use the most simple MIDIS dataset as example for its illustration. Its goal is to learn the representation and extract the features to capture the similarity and dissimilarity among the instances. The most representative case is autoencoder, right? Which typically learns entangled representation, wherein individual dimensions encode some unknown combination of features in the data. After that, autoencoder are required to have ability to learn disentangled representations, which goal is to extract features that correspond to distinct factors of variation, which means that the learned features should be independent to each other. So the variational autoencoder VAE was further proposed, which adds a probabilistic layer to the traditional autoencoder architecture, and it uses a likelihood function to model the distribution of the data, allowing us to sample from the learned distribution during the decoding process. VAE actually contains the best probability model of the data X and its latent variable Z. We can write the joint probability of the model as Pxz is equal to Px given Z multiplied Px. Now we think about its inference process in this model. Its target to infer good values of the latent variable, giving the observed data, or to calculate the posterior. Yeah, we need this posterior Pz given X. As we all know, Bayes' rule said Pz given X is equal to Px multiply Pz divided by Px. So the denominator Px is called evidence, and we can calculate it by integrating out the latent variables. Unfortunately, this operation requires explanation time to calculate because it needs to be evaluated over all the configurations of the latent variable. So we need to approximate this posterior distribution to save time. And this approximation process can be formulated with the model as that, and we approximate Pz given X with some models, with some Q phi Zx given Z given X with the neural network. So the Q phi Z given X belongs to a set of distribution parameterized by phi. So variation inference choosing the Q phi Z given X by maximizing the evidence lower bound, short as elbow. And this is akin to finding the parameters that minimize the carried distance between Pz given X and the P phi Z given X. Here is the detailed process of the elbow. The final equation is impossible to compute directly because the necessary evidence Px still appears in the divergency, right? Which is intractable as we discussed before. So by Jason's equivalent, we know the Kerr divergency is always greater than or equal to 0. This means that minimize the Kerr divergency is equivalent to the maximizing the error, like that. In this way, we are saved from having to calculate and minimize the Kerr divergency between the approximate and the exist posteriors, right? Instead, we can maximize the error, which is equivalent and computationally tractable. The physical meaning behind the error can be understood like that. The first term encouraged Q5 is given X to place mass on Z, and the second term encouraged Q5 is given X to be close to the prior distribution. And for loss function in VIE, and we can get the final objective step by step. Kerr divergency can be reformed as that, and the rewrite to joint probability, which is computable. Yeah, and then separate two items like that. And finally, we reform as the Kerr divergency item in intent. The first item means reconstruction error, and the second item means the Kerr regularization. Wherein the weight of it will change the degree of applied learning pressure during the training, so encourage different reputations. Some classic disentanglement works like beta VAE claim that if you want to learn disentangled representation, it's important to push a stronger constraint on the Kerr item. Yeah, because the Kerr item encourages conditional independency in the Q5 given X we have discussed before. Yeah. And here is the visualization results. We can see that VAE's representation are more semantically clear and more disentangled. Okay, let's look at some recent developments in disentanglement. According to the structure of disentangled representation learning, we can classify the DIR method into two groups, dimension-wise and vector-wise method. For dimension-wise method, generative vectors are fine-grained. I mean, one single dimension represents one generative vector, and those methods are always do their experiments on the synthetic and simple data set. And the dimension-wise method are mostly early theoretical exploration of DIR, and usually rely on the certain models like VIE and GAN. Yeah. For vector-wise method, their generative vectors are coarse-grained, and the different vectors represent different types of semantic means. The method are always used in real-world scenario, such as identity swapping, image classification, subject-driven generation, and video understanding. They are more flexible and model agnostic, I think. A typical architecture that can achieve dimension-wise the disentanglement is VIE. We have already talked about it before. It models that distribution, yeah, from the perspective of maximum likelihood using variation inference. So in practice, we usually maximize the evidence lower bound to provide a tight lower bound for the original log piece X. Generally, a standard Gaussian distribution is chosen for P theta Z, so that the Kerr term actually imposes independent constraint on the representations learned by neural network, which is the reason why VIE has the potential ability of disentanglement. Many improvements have been proposed by adding implicit or explicit inductive bias to enhance the disentanglement ability of VIE. The most we are knowing is beta VIE. Yeah, it's introduced a beta coefficient before the Kerr item in arable as regularizer to enhance the independence constraints. When beta is equal to 1, and it degenerates to the original VIE, and the larger values of beta encourage learning more disentangled representation while harming the performance reconstruction quality. So it's important to select a good beta to control the trade-off between the reconstruction and reconstruct quality and the disentangling performance. Balance the trade-off where many follow-ups are investigated, like the IPVAE, beta TCVAE, etc. Yeah, understand beta VAE propose an information capacity of C to guarantee the satisfactory reconstruction quality and also achieving good disentangled features. EIP VAE propose extra regulator to improve the ability to disentangle. Vector VAE use total correlation to directly impose independence constraints, and the other also known here, and we did discuss them all. Okay, generative adversary net again has another important generative model proposed by Goodfellow et al. Has also drawn much attention in the past recent years, right? For disentanglement, InfoGAN is the first one using the GAN paradigm to conduct dimension-wise DIR. It leverages mutual information as constraint to encourage disentanglement, but the performance of GAN-based method is consistently reported to be lower than VAE-based method. And the extension region of InfoGAN is a self-supervised minor, and it adds constructive learning-based regulator as that. ACGAN is also built upon the InfoGAN, which employs a spatial constriction module design implemented as a spatial mask to enforce the focused areas to be more simple and pure. Furthermore, considering the powerful generation performance of GAN, GAN-based model are also be used to achieve vector-wise DIR, a more real-world task like DRGAN. We use the two vectors to represent identity and pose, respectively, for pose-irrelevant face recognition. This framework is for activity image-to-video retrieval, which separates video reasoning, video representation into a vector-wise appearance and the motion part. Yeah. Similarly, DRNet disentangles each video frames into a time invariant and time relevant component. This disentangled representation can be applied in further frame prediction or classification tasks. Recently, a powerful diffusion model have been widely used in generative tasks such as text-to-image generation and text-to-video generation, right? And diffusion models also benefit from the strengthening of vector-wise DIR, like this model, like this work. Both propose the disentangled but stable diffusion by tuning framework for subject-driven text-to-image generation by disentangling the feature into identity-irrelevant branch and identity-preserving branch. They use a clip text encoder to extract the features and embeddings and use the adapter to separate them. Yeah, one for background and the other for the foreground. They show that the non-by-tuning method, elite, and the image editing method like structure, instruct pixel struggle in preserving the subject identity, and the popular dreamballs of Google. And we also familiar with that. They suffers from the overfitting on the input background, and also overfitting to the subject identity changes. But the proposed disembowels achieves better performance in those aspects. Yeah. So dimension-wise or vector-wise, the DIR is better. It depends on the number and the granularity of the generative factors you hope to consider. For example, in many real-world applications, we only need to consider two or several coarse-grained factors. The dimension-wise vector are mostly earlier theoretical exploration for DIR in some simple datasets. So in recent years, researchers focused more on how to incorporate vector-wise DIR to handle real-world applications. So it may be a trait to explore the powerful vector-wise DIR in the realistic. Okay, all of the above mentioned DR method holds the assumption that the architecture of generative factors is flat. I mean, all the factors are parallel and at the same abstraction level. For example, VRVAE disentangle the factor, disentangle the face, rotation, smiles, and skin color on the celebrate A dataset. And the info again also disentangled elevation, lightning, etc. on the 3D face dataset. But in practice, generative process might naturally involve hierarchical structure, right? Where the factors of variation have different level of semantics. For example, the factors controlling the gender has a higher level of abstraction than the independent factor controls the eyeshadows on the celebrate A dataset. So many works have been proposed to achieve hierarchical disentanglement. This work of iClear 2020 presents a strategy to progressively learn the independent hierarchical representation from high level to low level. And this model starts with learning most abstract representation and then progressively grow the network's architecture. I mean, to introduce more representations at different levels. Yeah. And the Fingan proposed unsupervised hierarchical disentanglement framework for fine-grained object generation. They designed 3 latent representations for different hierarchical levels, including the background code and parent code and child code, which representation background, object, shape, and object appearance, respectively. And background is the lowest level, followed by shape and appearance. Fingan statewise or set progressively image generation achieves better controllability based on such hierarchical disentanglement idea. Yeah. On the other hand, the object can be described as a combination of primary vision attributes. Disentangling such underlying primitives is a long-term objective of representation learning. Yeah. Similarly, HiSD achieves a fine-grained image-to-image translation by organizing the labels into a hierarchical tree structure, like showing here, in which dependent targets, inclusive the attributes and the disentangled styles, are also located from top to bottom. Yeah. CapsuleNet, yeah, was introduced by Hinton et al., which inherently has the potential to achieve a DIL for their hierarchical part in the whole architecture, providing framework for learning disentangled representation. And the beta CapsuleNet was also further proposed to learn disentangled capsule by adding the information bottleneck constraints like that. The results show that it has a better ability to learn disentangled representation than beta VAE and the original CapsuleNet. Because a capsule VAE considered the relationships between the factors of variation in the data from the perspective of causality. Yeah, describing these relationships with scene graph, like shown here. This work also introduced the disentangled causal mechanism. They explore capturing independently controllable factors of variation in the data. This means that the learned representations should be used to control the individual factors of the variation without affecting others. This means it's the same with the VAE target. They prove that causal VAE successfully learns the representations of causally related concept and allows intervention to generate counterfactual outputs as expected according to our understanding of the causal system. Okay, let's summarize some milestone work about mentioned. The disentangled definition is proposed by Benjo in 2013. Of that, to achieve disentanglement, some works try add extra regularization to generating models, AI again, and even recent popular diffusion, right? And which works can be classified into vector-wise, dimension-wise, flight, hierarchical, or causal-based range. And except that, DeepMind also developed a group theory-based definition of disentangled representation. Our next speaker, Yang Tao, will introduce it with more details. Yeah. And recently, we revised the previous disentanglement work and give a summary, give a claim that at least 3 unresolved issues are left. Yeah, they all have heavy reliance on the label notation and the synthetic data, and they all depends on hierarchical or handcraft disentangling constraint and lacking reasonable evaluation metrics. So we propose our new disentangle framework compared to VAE-based, GAN-based, diffusion-based, and our proposed is a closed-loop approach, leverage 2 kinds of generative branch to build a cycle system for mutually promoting, which different from the previous work, all rely on the heuristic handcraft loss constraint to infer disentanglement. Yeah. Basically, we construct our unsupervised closed-loop disentangle framework based on a diffusion-based autoencoder backbone and combined with the Copilot beta VAE like that. To collaborate to branch well and help future disentangling, and we encourage diffusion AE. We encourage our diffusion AE autoencoder and beta VAE to complement each other, achieving a win-win effect. We first use a pre-trained latent VAE to guide a semantic aware reverse diffusion process with distinct knowledge distillation loss, and then the greatly increasing information capacity during the diffusion process is taken as a feedback in turn, to progressively enforce the inner latent VAE more disentangling. With this framework, we can control the image generation to make a face smile while keeping the other attributes same. Okay, then we gonna transfer our attention to the other important concept that recently popular, vision models compositionality. As we all know, people understand the world as the sum of its parts. For NLP, people can understand and generate more sentence with word, and the sentence is composed of serious words, right? Besides, as shown right, our natural animal and the plant can be broken down into pieces, and our real world and the natural life tree is hierarchical, right? When presented with the new concept, people can decompose this novelty into familiar parts. Our knowledge representation is naturally compositional. So compositional learning refers to combine simple primitive concept to understand a complex concept. This idea was proposed in the vision domain by Hoffman in 1984. So for computer vision, we humans typically leverage compositionality to efficiently learn a new concept, understanding how familiar parts can combine together to form novel objects. Our human can understand a potential infinity numbers of things by combining the objects, or learn about new objects through the combination of part and the relationships. So look at this example to understand compositionality, how to combine these two concepts of hawk and robin. Actually, we have many choices, such as a hawk with the red breast of robin and a hawk that preys on a robin, right? So this means that different composition will lead to different results. Take ImageNet that we all know as an example. It's a classic hierarchical image dataset. The entity can be decomposed into artifact and the plant. Artifacts can be further decomposed into structure, framework, window, etc. More cases are shown here. Our objects can be seen as the sum of deformable parts, and many separate individual objects can further together represent the new scenario, right? When we perform vision tasks like object recognition, and its generalization ability will be largely influenced by the object compositionality. Besides, Conversational human pose regression or estimation also benefit many human-centric recognition tasks like personality and tracking. Moreover, events can be formulated as a sequence of actions or grounded object deformations, and also a good sub-action recognition could benefit many events on the same task. And the planning can be regarded as a composition of hierarchical goals and some complex tasks like auto-driving and robotic navigation should I believe should revisit the issue of compositionality. The most common case is block game, right? We often play in our childhood, which uses simple vision elements such as building blocks to train children's visual perception ability and the spatial cognition ability. So in summary, human vision compositionality is considered one of the most fundamental ability. Shared attributes are clustered to form basic categories, and the compositionality of attributes defines the category inclusion relationship. And then we present an overview of recent development in this topic. Actually, many civil applications can be enhanced by visual compositionality, such as action classification, vision grounding and retrieval, question and answer, and so on. For action classification, action like drinking from a cup of tea and taking a notebook, highlight and labeled. In the middle is the image with SIGGRAPH annotation for object and relationship, also illustrating how object grounding and image retrieval can be improved by compositionality. For vision question answer task, the question about the image also asked and answered based on the composition of object and their attributes. Overall, this case all demonstrate the advantages of using compositionality in different CV tasks. And for the most popular field of vision language model, the challenge about compositionality still exists. As shown in this case, the encoding of compositional relationship between the object and their attributes in text or images may be always not so accurate. The grass is eating the horse, and the horse is eating the grass. They are both right in the eyes of VRM. That's ridiculous, right? For the compositional text-to-image generation, the existing method also hardly compose concept into a right scenario. We can see that the first two images are correctly generated according to the text description, but the third one does not match the description. So this paper proposed T2I CompoBench, a comprehensive benchmark for open world compositional text-to-image generation, which consists of 6,000 compositional text promos from 3 categories, such as attributes, object relationship, and also some color, shape, texture, spatial relationship, and a complex compositional minor. This benchmark also inspires some new approaches for compositional text-to-image generation, which training free from work named RPG, using the powerful chain of thought reasoning ability of the multimodal LLM to enhance the compositionality of text-to-image diffusion model. This paper proposed the Compose Agent, a training-free approach for compositional text-to-image generation with a large language model agent as its core. Its fundamental idea is also based on a divide and conquer solution, and is similar with compositionality. In summary, compositionality is really, really important for visual content generation. Except the very popular AIGC, its concept can also benefit many realistic applications, such as self-driving. This method called Mars, I think I remember, develops a realistic sensor simulation that plays critical roles in solving the remaining corner case by simulating them. Yeah, Mars models the fine-grained instance and background environment separately and use the separate nerves. So the object statics, such as size and appearance, and dynamic attributes such as trajectory can be rendered in compositional manner. Yeah. This enables the simulator to support object-level compositional editing and enable interactive editing, such like that we can delete, aid, or edit the movement of the vehicle instance, etc. So simulating a large numbers of corner cases that are difficult to collect in reality and providing the corresponding solution for the self-driving algorithms. Another case is very popular recent, sim to real-based embodied AI. For example, GapNet proposed to learn generalizable object perception and manipulation skills by compositional parts and present a large-scale interactive dataset with rate part annotations. Such part compositionality both cross categories object manipulation and can transfer embodied AI system to real scenarios. Recent process in using large language model LLM as high-level planners has also shown that the complex task can be reduced by decomposing them into primitively labeled plans, making it possible to generalize a novel robotic task in a composable manner. Yeah, as shown above, by further incorporate visual knowledges from the LLM by instruction tuning, vision language model becomes well suited in the robotics tasks, which can solve the limitations of the convention method. Yeah. Despite advance of LLM, how to evaluate their generalization ability is still under explored. I mean, we can also draw some inspirations from the human vision compositional abilities by extracting the compositional commonalities of objects. We can construct category representation and classify new categories with LLM. In this manner, we can well evaluate our LLM. And this benchmark of combo, as known as the compositional block games, evaluate LLM's performance from the three aspects of pattern perception, abstraction, alignment, and category buildings. Yeah. So next is about the SynGraph as a good way to reflect compositionality. We think we will introduce it in details. In this case, for this image, when we ask what is happening in this picture, we need to identify the objects in the image as well as the relationship among them. I mean, for men, women, and cat. Firstly, the AI system might answer that to person, camera, cat, doll, and the earring. With more detailed annotations, this paper, following the compositionality thinking, present the vision genome dataset to enable the modeling of such relationships. The women in the white dress and the ears is feeding his husband cat, and they are very happy. And one person is take pictures with the camera, and there are some yellow and adorable dolls on the cat. It seems to be on a waiting sense. Yeah. Besides, the visual genome datasets also collect dense annotations of objects, attributes, and relationships within each image to learn these models, which regularize the objects, attributes, relationship, and noun-phrase in region descriptions and the question-answer pairs. So we can see that relations between the objects must be coded into the gist. That means vision compositionality should encode the relationships. And then vision genome dataset was exactly built for compositionality, which composed seven components like region description, object, attributes, relationship, region graphs, scene graph, and QA pairs. Here we show some examples to review to show that. Another demo of visual genome dataset has been shown here. Each image contains region description that describe a located portion of the image. They collect two types of QA pairs. One is freedom QA, and another is region-based QA. And each region is converted to a region graph representation. And finally, each of them is composed to form a scene graph with all the objects grounded to the image. The left work shows the scene graph is an effective representation for very detailed image description. They present a rule-based and classifier-based scene graph parser whose output can be used for image retrieval. The right work present a new scene graph hallucination mechanism for effective abstraction text-to-image synthesis. All the papers of CVPR and NeurIPS last year. Yeah. In addition, a model that detects vision relationship should also be able to perform, zero-shot prediction is never seen before. As shown here, the model that has seen many examples of person, sit chair, and few samples of hydrant on the ground. With the compositionality, the model could recognize the unseen composed scenario of a person sit on the hydrant. The benchmark of action genome dataset was proposed. So it contains many actions about spatial temporal scene graph, and also capture the changes between the object and their pairwise relationships. This benchmark of action genome is that modeling is to model the temporal changes in relationship, and can be further improve the inference. Like that, when we capture the temporal changes of not contacting or sitting on the video frame, the top three prediction results will become more accurate compared to the original baseline. These relationships between the entities carry semantic meanings. Also helps view to differential between the instance and of the image. For example, in this image and the football match, there may be multiple persons present, but each one is for different relationship. One is kicking the ball, and the other is guiding the goal. Yeah. Scene graph composition is also helpful for the complex image generation. In this work, as shown in we can see here in the failure case of daily E, and giving the complex text promote a shape by another shape and a boat on the grass. The model hardly generates accurate object relationship or quantities, but our proposed scene graph-based method could do that. So we propose to use the scene graph representation by jointly modeling the disentangled layout and semantics with VAE and the diffusion models. Then we inject the object-level condition of layout and semantics to guide the visual image composition following the scene graph descriptions. In this way, our method shows great superiority in many aspects. For example, our disco well clarifies the relationship between the boat and the grass in the first line, and also the semantics of bus and building in the following lines. Yeah, the symbols in the last line also showcase our method could precisely generate the right quantities of objects. Compared with other scene graph-based generation method, our method also improves the quality of generation. We also demonstrate the generalizable generation under consistency for graph manipulation, such as node addition and attribute changing, like color change, like that. So visual compositionality are everywhere. In many fields, intelligent agents need to develop compositional understanding that is robust, generable, and powerful. Many well-known techniques also contain the core idea of compositionality. Also pay attention on how to efficiently leverage such informative relationships. Yeah. Many tasks can be benefited by compositionality as well, including but not limited on explainable AI, human intention, VQA, social relationship, and so on. Yeah, we should revisit the idea and reflect on the future direction of compositionality. Okay, then I want also discuss the relationship between the two concepts we discussed before, between the disentanglement and the compositionality. Rofo started a study on their Europe 2022 pinpointed that simply increasing the pressure to produce disentangled representation, just like increasing beta in beta VE, produce representations with worse generalization. Its finding also demonstrates the gap between pursuing the better disentangled feature and more generalizable representations in previous studies. So last year, Yang et al. Provide an important insight. Vector-wise representation, I mean, use a vector instead of a scalar to represent a concept is the key to empower both the disentanglement and the strong compositional generalization. This insight also shows that our brain encodes the information in neuron population activity rather than individual neurons. And many results for both the compositional generalization and the disentanglement performance can demonstrate that. And more details, our co-organizer Yang Tao will present and explain in the follow-up notes. Yeah. Next, we see another application, which courses actually also inspired by disentanglement and compositionality. It means they're compositional, they're short learning. Yeah, its goal is to learn vision concept like attribute and object from scene composition and combine concept knowledge into on-scene compositions. The key is learning the disentanglement of the attribute object composition, as shown here. Giving the images from the scene attribute object composition, humans can disentangle the attribute yellow from the yellow bird and the yellow here, and the object flower from the purple flower and the red flower. After learning the visual properties of this concept, humans can then recognize the images from the on-scene conception yellow flowers. Composition yellow flowers, yeah. Here is the method overview, and we didn't go to the details because yeah. Another paper that published at the CPR 2022 also studied the problem of compositional zero-shot learning. They used the vision disentangled feature to hallucinate the bending that are representative for the scene and the novel composition to better recognize the learning model. And multi-head key value attention is a backbone of the wide successful transformer model and its variant, which has two fundamental computations: search and retrieval. And these papers also evaluate such two properties and propose compositional attention. They disentangled search and retrieval and compose them together in a dynamic, flexible, and context-dependent manner. Yeah, it outperforms standard multi-head attention on many tasks, including some OOD setting. Finally, we use some practical applications for brainstorming the future development of disentanglement and compositionality. Here, D and C means the disentanglement and the composition. Yeah. First possible case we want to discuss is also the generation, different from the existing method using captioning techniques to get disordered or set entangled text space. We propose to use the semantically clear text descriptions as disentangled expression with the help of large language model, and design different semantics that identify and guide latent factors hidden in the observed data, and thus get the interpretable and clearly disentangled textured representations. Then we enforce the disentangled visual features and the textual features for alignment, such like that. If we change the corresponding attribute just like this, changing the coded color from yellow to red, only the visual feature that also present color attributes will accordingly change. So we get isolated property change result. The whole process can be optimized with the dual consistency loss, like shown here. Based on the cycle loop, the framework feature space will finally convert to an optimal disentanglement state. And this work focused on solving the hybrid distorted image restoration. And the existing, as we all know, existing image restoration method often ignore the inherent interference among the hybrid distortion. So to disentangle such interference, we can we introduce the disentangled features learning to achieve the feature level divide and conquer solution. Yeah. The main idea is to use a channel-wise feature disentanglement to increase the discrimination between hybrid distortions. Here are some subjective quality comparisons showing that our method outperforms other sort of methods at the same time. Yeah, and those fingers show the visualization of correlation metrics between the channels from the feature before and after the feature disentanglement module. Yeah, we can see that the module reduces the channel-wise correlation by disentangling the feature. And this work also focuses on solving the real-world image super resolution, which is composed of many kinds of distortions. So, and in real-world image super resolution also need disentanglement and deal with each distortion separately. In frequency domain for super resolution, the degradation also in the high frequency components. So, but for real-world super resolution, the degradation exists in all the frequency domain. So we need to disentangle. Yeah, we design the all frequency region adaptive framework with frequency decomposition and the compositional modeling and the composition module, and achieve the best performance at that time in terms of PSNR and SSIM. Similarly, we also try this idea of disentanglement and compositionality in the task of person real ID, and we generate safe augment based on the disentangled results, and so help model training with more diverse and reasonable samples. Here is the overview of the method, and we'll also go into the details. Similar solution is also existed in depth estimation task. Yeah, this work SR DepthNet first disentangle the content representation and use it for depth estimation. And its structure information is the key for depth, so we need to disentangle it and highlight those information in the following estimation process. We also apply this idea in depth estimation, and this work is the first one to fuse geometric representation and EV representation as the disentangled and the complementary features. So they together to handle the geometric ambiguity in 3D SSC semantic scene computation. Another work of ours also uses this idea to handle depth estimation and propose a new concept of volume probability distribution security. Yeah. And this work, named as Navy Nerve, is the first work that explore the 3D disentanglement at feature level without any priors and supervision. Its task arms to identify and decompose, manipulate the underlying factors of the 3D data, which helps AI fundamentally understand our 3D world. And we use NERV as the differential 3D representation and introduce the self-supervised navigation to identify the interpretable semantic interaction in the latent space. And take full advantage of both latent semantic navigation as our outer branch and the NERV representation as the inner branch in a complementary manner. So the outer branch learns to identify semantic directions for global disentangled representation, and the inner branch learns to focus fine-grained attributes. And the Navy Nerve outperforms some 3D aware GAN-based works, including PyGAN, Giraffe, and Standard, in attribute manipulation. So furthermore, the model also obtains comparable performance to editing-oriented models, which relies on semantic and geometry priors, especially on the facial editing-related dataset. And the demo and the code are also public. The last one is about image compression, with a task that related to information processing. And we proposed a disentangled and composable image coding for machine tasks, which design an internal adapter to enable parameter efficient transfer to different machine tasks and consider the correlation between the different machine tasks in a composable manner. Yeah. Okay, as a conclusion, we think that disentangled representation learning is a fundamental task, which is the key for general AI, and compositionality is another important foundation for diversity and scalability as the era of large models. And many challenges and opportunities are still existed, and many practical applications could be improved by such core ideas. Yeah, okay, so thank you very much for attention. This is the end of the talk. So because my talk takes so many times, so if you have any question, and we can discuss offline at the coffee break. So we welcome our next speaker, Professor Deng. Yeah. 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 Hello, hello, hello. Tom, can you hear me?
Yeah, I can.
Yeah, I think you can share the screen, and Professor Zheng will speak offline. Okay.
Okay.
It's full screen. Yeah, full screen. So
Okay, you see my screen?
Okay.
Good. Good morning. So I'm Wenjin Zhang from Eastern Institute of Technology, Ningbo, China. So I guess Xin just gave a pretty good overview of disentanglement and compositionality. In the second part of the tutorial, Tao Yang, and myself are going to give talk on about the disentangled model-based visual concept learning. So this is a particular way of doing disentanglement, and in fact, Tao is supposed to be the main speaker, but he couldn't get the visa in time, so but he's online. So the plan is to, I'm going to, Tao, can you move forward one page?
Okay.
And so I'm going to give a very brief introduction about the background and the motivation for this particular type of approach. And then Tao will take over after that and explain more details about some of the more some of the approaches that have been proposed in the past couple of years, as well as provide discuss some future work. Next. Okay, so we know that AI has experienced tremendous growth in the past few years, thanks to the rapid development of deep learning technologies, and especially the generative large models in the past couple of years. And so, slow down. Can you go back one page?
Okay.
Yeah, and so there are some debate about whether we have seen the spark of artificial general intelligence. Someone said that it's already there in the large language models, but some others says not yet. We need to use the world model-based approach in order to achieve that. Next. So in the world model concept is proposed by Kun, who basically suggests that we should start with a system that can learn how to how the world works, just like baby animals. So we're basically moving from machine learning to learning machine that can learn. So the world model can be constructed from the observations from the environment, based on which then we can perform actions. So next. Right. So for example, the visual model is part of a world model, right, that can encode the high dimensional observation into low dimensional latent space. So the visual concept, the language concept, and the combinations, right, can form part of the world model, and based on which we can conduct actions. Next. Right. Now, we know that the large language models, such as ChatGPT, can provide answers to our questions in a pretty powerful way. But we don't know how exactly it works, right? So there have been some study that is trying to, study about the concept mechanisms in large language models. Next. And it has also been shown that concept learning can help cognitive science. That by working on the brain data of monkeys, it is discovered that we can learn monkeys can actually learn the concepts of locations and directions. Next. Right. So the visual concept learning was proposed by Hinton, who suggests that concepts can be represented by distributed patterns of activities in networks of neural-like units. And the advantage is that it's good generalization. And one particular way of doing visual concept learning is disentangled representation learning. which is a concept proposed by Benjo in 1993. And Benjo basically argued that for AI to fundamentally understand the world around us, it must be able to identify and disentangle the underlying explanatory factors hidden in the low-level sensory data. And so if this can be done, then we can, if we change the explained factors independently, and through a decoder, we should be able to see the reconstructed image with the corresponding attributes being changed. And then we can also design an encoder that can extract those explanatory factors from the images. Next. Okay, and so the objective of disentangled representative learning is to empower existing AI models the ability of human-like concept induction, and better, develop a unified foundation model to achieve hopefully artificial general intelligence. Next. But we are facing a few challenges here. One is that it's not clear how our human brains perform the induction. And second, the image data is pretty complex. There are things like occlusion. There's complex scenes, complex concepts, make it very difficult to handle. And there's also difficulty of obtaining human labels. There are just too many objects, too many concepts. Next. So these challenges result in poor representation and sometimes also poor generation qualities in the existing AI models. And so in the past few years, we have developed a few solutions that are trying to address those problems. Some are more theoretical basis that are trying to provide some theoretical guarantee. Some others are more practical, trying to solve for example, the trade-off between the generation quality and the representation quality, and also to unify the disentangled representation learning and object-centric representation learning. So I'll leave how to explain more details about some of these approaches. Tao, go ahead.
Okay. Thanks for Professor Wen Yunzhen to introduce the background part of this talk, and I will continue to introduce my works in the following sections. And our target is to embed real concepts into AI systems by disentangled models. So how we embed these real concepts? There are two different kinds of ways. One is explicit way, and this is done by network structures. And the other is the implicit way. We can design different regularizations for the models to solve the poor representation and the poor generation ability of the model and improve the disentangle abilities. So we can, by this way, we can push the boundaries of this topic from fundamental to application. And the explicit regularizations can embed the inductive bias from the cognitive model, and also the implicit network structures also can inspire the research of cognitive science. And I will introduce my first work, which is published in iClear 2022, group theory-based disentangled VAEs. Inspired the symmetry in physics that can reflect objects' nature, Higgins proposed a group-based definition, which is a formal and rigorous mathematical definition of faithful representation in definition 1. However, since the definition requires group action in word state, which is always not accessible for us because it is ground truth, and we want to develop an unsupervised method. So this inspires us to ask, how would the definition benefit unsupervised representation disentanglement? And in this research, we proposed a theory-based method, which is inspired by the dihedral group, which is from group theory. Dihedral group is a is a group of rigid motion of square, which forms a fourth dihedral group. The motions can be composed to basic ones. One is rotation, and the other is flipping. We regard the vertices as images and the vertex permutation as image-based, model-based image transformation. So we can use this kind of method to replace the group action in W space into observation space, as the equation shows. Considering a set of images, we first encode the image into a set of representations. We then conduct group actions in the representation space as a permutation of images. These permutations can form a permutation group, which is defined by the model. So we can impose constraint on this group. So to impose constraint on the model. Therefore, we propose a theorem proved by group theory. We first give two conditions for the existence of this agent group. Then we derive additional constraint 3 to achieve such disentanglement. The theorem depicts three constraints for disentanglement. One is structure constraint, which indicates the agent group should be isomorphic to the group predefined. And the second is a data constraint, which indicates that the variations in the data should be generated by some basic generators. And the third is a model constraint, which means the group element should be defined as encoding, action, and decoding. So how we implement this group by a model? This requires such a mapping should be differentiable, because we need to back propagation to optimize the parameters of the network. And the other is we want to mapping the representation into an isomorphic group. So we propose to use Euler's formula to map the representation into some kind of group, which is nth root group. So how we achieve such an isomorphism? We propose two regularizations to achieve such an isomorphism between two different groups. One is for commutative, and the other is periodicity. For commutative, we call this loss as abelian loss, because in group theory, commutative group is abelian group, and the other is order loss. From the name, we know that it's a constraint for element orders. And with these two additional regularizations, we can constrain 8 VEs with disentanglement requirements. And from the table, we know that the four different VEs which is groupified obtains a better disentanglement performance. To understand the gains brought by this model, we visualize the 3 dimension of the learned representation space, which corresponds to positional X, positional Y, and Z. We can observe that the space learned by the original VAEs collapse as this row shows, and the groupified VAE has a better representation space as shown in this row. This is because the regularizations plays the role of self-supervision signal, so suppress the representation space distortion. And if you're interested in our project, you can scan the QR code for the GitHub implementation, also the open review. And I will introduce my second work, which is published in iClear 2022. The motivation is that the existing disentangled models suffers from two different challenges. One is a trade-off between the disentanglement and the generation, and the other is disentanglement constraint is not sufficient for disentanglement. How to solve these two different challenges? We propose to use pre-trained generative models to obtain the disentangleability. Meanwhile, keeps the generation ability. If we can find the directions of distinct image variations, for example, one change the background color and one change the object color, then according to the goal of disentanglement representation learning, the directions can be treated as these factors. To learn disentangled representation, we use an encoder to extract the representation from the generated images. In this way, we propose our method Disco. Given a pre-trained degenerative model, we fix it, then use a navigator to generate different image pairs. Then we use disentangled encoder to extract the representation from image pairs. To model the variation between the image pairs, we build the variation space based on encoded representations. By pulling together similar variations and push away different variations, we jointly train the navigator and the encoder. To make the navigator discover distinct direction and the encoder extract disentangled representation. From the table, we can know that Disco achieves the SOTA performance on different the three datasets from two different metrics. And we can have we can observe that Disco can learn some concepts like expose, smiling, and the color of the cat and the eyes of the cats. If you are interested in this project, you can scan the QR code here to learn more about the implementation details. And however, the former method, the method I introduced before cannot handle the pre-trained diffusion model. So how can we solve the disentanglement of pre-trained diffusion model? We can define such a problem that we assume the dataset was generated by n different generative factors, which is corresponding to one conditional probability and one probability corresponding to a submanifold of the data. We can see from the equation that the data distribution can be integrated by the factors one by one, and if we can model this kind of problem, we can sample the data from each submanifold. The submanifold was corresponding to one semantic. For example, the purple submanifold indicates that the images are the image's object color is red. So the images from this manifold, the object are all red. And how we obtain the gradient field from this submanifold? We can use the Bayes rule to decompose the conditional probability into two different parts. One is a pre-trained generative model, the UNet provides, and the other is our target. We want to learn this this gradient field to generate the samples from the manifold. However, this gradient field have to know the conditional factor FC, which is not accessible. Fortunately, we can use a disentangled representation to provide an alternative for this F. This require us this has two different requirements. One is completeness and the other is disentanglement. With these two requirements satisfied, we can use the representation conditional distribution to replace the factors conditional distribution. So how we achieve such two requirements? We can observe in the figure A that this is a PGM of the whole process. The representation is obtained by the observing data, and this structure means that these representation are conditional independent, which indicates that the probability can be decomposed into a product of different probabilities. And we need to if we obtain such a gradient field, we can use distribution shift to sample the data from the manifold. And we propose to use such a reconstruction loss to estimate each gradient field. Why would we need to do such a approximation is because the gradient field is computational expensive. We cannot afford such a cost. So we use several decoders to estimate. And how we achieve disentanglement requirement? We can use we can propose a mutual information estimator by this proposition. And this proposition can translate into two different conditions. One is invariant condition, and the other is variant condition. By translate into these two requirements, we can obtain two regularizations. However, for different model, it is not so, the sampling, it is not so efficient. So we use Tweedy's formula to get one-step estimation of the observing data. And so we can calculate the loss functions at each training step. From the table, we know that DSTIF also achieves the SOTA performance, even comparing with the previous SOTA disco. And also, it learns the pure factors like background color and azimuth and floor colors. The one special ability of this model is that the because it models each submanifold, so it can sample data from the submanifold, which is corresponding to the same factor. And this is also can be applied to real-world data like the Celibar images here. And if you are interested in this project, we also provide the GitHub link by the QR code and open review. And in the next section, I will introduce our paper, which is published in NIPS 2022. The motivation is that obtaining the human-like perception ability of abstracting visual concepts is always been fundamental and important, but there isn't any algorithm that can achieve this goal. And we are particularly interested in finding a general way to learn visual concept from pixels, which covers two branches. One is concepts like attributes, and the other is concepts like objects. So this corresponding to two different areas. One is disentangled representation learning, and the other is object-centric representation learning. And if we can encode these visual concepts into a set of tokens, these tokens can be similar to word embeddings in NLP. and so it's better for some cross-modality tasks. To achieve the goal I proposed before, we need to reformulate the problem. So we define two different kinds of representations. One is concept prototypes, and the other is concept tokens. For concept prototypes, these representations should be embedding of different different meta concepts, and the meta concepts is a vectorized embedding, and it is a dataset level concept. For concept tokens, these representations is image level representations, and the embeddings are and these sets of embedding can represent an image. So what is a good concept prototype? What properties we expected they have? For concept prototypes, they should be disordered set that can query concept from value from the data. Also, for concept tokens, they should be disordered set because concepts itself is disordered that can decode back to data. Most important of all, as a requirement of disentanglement, the extraction of each concept tokens should be independent. According to these definitions and the requirements, we design the VCT encode as follows. By using pure cross-attention here, we guarantee that the extraction of different concept tokens is independent. In addition, we do not add any positional embedding for the representations to keep the disordered requirements. Similarly, we designed the VCT decoder by symmetry as follows. In order to fuse the information of concept tokens, we adopted self-attention layers for concept tokens. And for injecting fused information, we adopted cross-attention modules. Overall, the network structure is shown in this figure, and we can use this network to constrain disentanglement from image to representation and image. However, if we want to impose disentanglement from the perspective that representation, image, and representation, this framework doesn't work. So we propose another loss to impose disentanglement in this process. we can swapping the representations randomly for each token and recognize the swapped token on the decoded images. And this process can achieve disentanglement in this process. From the table, we know that this new framework achieves a new SOTA for the disentanglement, comparing the previous baselines. And this framework also doesn't have the problem of poor generation because adopting the VQVE as a pre-process module. And we can observe that this model also can process data, since data, because this requirement doesn't require the factors should be attribute or objects. So objects also satisfy these requirements. So when we adopted this method in objects datasets like Clever, our model can decompose the scene into several objects, and thus we can add an object once a time, or we can decompose a scene into several different objects. And also we can compose two objects from two different things. And for real world data, we also can adopt a stronger encoder to achieve disentanglement in COCO dataset. As shown in right figure, VCT learns concepts like sky and floor. And VCT also have the ability to achieve disentanglement in class datasets such as ImageNet and LSUN CAT, like FFHQ and LSUN Church. To achieve cross-modality disentanglement, we can adopt a CLIP pre-trained image encoder as our replacement of VQVE. And by train such a model, we can simply replace the encoder into a text encoder and achieve the function that text-based image editing or text to image. If you are interested in this repo, you can also scan the QR code here. And I will introduce the last work of mine is a diffusion model based disentanglement. The previous introduced methods all rely on some regularizations. This kind of reliance is not what we wanted. So we want a model that doesn't need any regularizations. And we observe that in stable diffusion, the words has a strong correspondence to the spatial attention maps. So how to leverage such a phenomenon to learn disentangled concepts is a problem we interested. And we can imagine that we have an image encoder that encodes the image into several concept tokens, which is similar to text to image generation process. And these tokens serves as a role of the conditional signal of image generation. And this conditional process is implemented by cross attention. In this cross attention, the spatial features plays a role as a role of query, and the representations plays a role of key and values. And by this structure, the diffusion model itself can be a disentanglement inductive bias. And another inductive bias is the diffusion model theory, because diffusion model the loss function can be rewritten as a formula like this. And this kind of formula is very similar to annual VE. Annual VE is KL term here. So for different time steps, there are different information bottlenecks. And this information bottlenecks can serve as the factor selector. So we can use this mechanism to disentangle different factors by using different time steps. And from the table, we know that the new proposed methods outperforms previous SOTAs and achieves a new disentanglement performance. And also for Celibar in human face dataset, INCDIF can achieve better disentanglement results and generation results. These two metrics corresponding to two different abilities. And for the toy dataset here, it also can learn some pure concepts. And we can observe that for the attention maps in INCDIF, it also appears that the correspondence between the learned representation and spatial cross attention maps. And compared to the previous SOTA DISTIF, INCDIF can learn more concepts and more pure concepts. And we can see from the table that different schedules always leads to different disentanglement performance, which verify our assumption that the schedule, the diffusion model itself plays the role of disentanglement. And if we replace this diffusion model into a normal decoder, the performance has a catastrophic fail. And if we replace the softmax into an ADA group norm, the performance also drops significantly. And compared to the previous SOTA, DISTIF, INCDIF can use less parameters and less flops to achieve better disentanglement. And to summary our talk today, we propose 4 different kinds of methods from 2 different aspects. One is explicit regularizations, and the other is implicit network structures. And for future work part, we think this work has done some fundamental tasks like disentanglement theory and generative-based disentangling. And in the future, we need to more focus on applications such as generation and disentangled fundamental model, unified fundamental model. And the second is entanglement in cross-modality generative models. And the third is generative model for real concept. And thank you. In the next, let me give my time to the next speaker, Dr. Song. Thank you.
Yeah, thanks again to Professor Zeng and Yang for the great talk. And because we little over time, so I suggest we skip the coffee break. So next speaker is from Professor Mikkel.
Okay, so
can you see the screen now? Hey,
yes,
Nico.
we can. Yes.
Okay.
Okay, so we'll try to have less slides this time. So we are going to be slower in some sense. This is some work that we have been doing together with my student UM, and practically what we want to do now is to give a connection between equivariant as a disentangled representation learning. So this is something quite interesting. So we are looking into several transformations that could be equivariant and could lead you towards disentanglement. So what I'm going to do, I'm going to have a short introduction about this concept and how they are connected. And then Yue will present some of our work. And this is kind of a transition. So we started to work on this on, well, so we have the first paper at ICML, then it was an EURIPS, and now it's a submission in TUPAMI, which are connecting these concepts. So one of the interesting part is that, and this is what Yue will present, we also try to model the latent space as a flow. So we try to look at some physical processes and see how we can use this information so that we can achieve disentanglement by design in some way. Okay, so I thought that maybe at the beginning it's good to have some ideas about, let's say, what would be this equivariance, right? And if you look into Wikipedia, I just copied from there. There are this kind of very broad type of, let's say, definition in which you talk about symmetry for functions, and they also need to define a symmetric space. And then this function is said to be an equivariant map when its domain and codomain are acted on by the same symmetry group. Okay. And then, of course, when you have this function commutes with the action of the group, right? So in other words, we are applying symmetry transformation and then computing the function produce the same results as computing the function and then applying the transformation. I'll have the formal, let's say, definition in the next slide, but I just wanted to have it more like in the, let's say, in the text in this. One of the interesting part is that this connection between equivariance and invariance, okay? And this is what you see in there. You have this equivariant mapping, so you have a function from X to the Y domain. It says to be equivariant is f of G and X, it's equal to G times f of X, right? So if you see there in the image below, you can have different type of transformations. So you can, for example, do some reflections of the image. If you do the segmentation, then also the segmentation map will have to have the same property of reflection, right? So this is the equivariance type of things. Or you can also do things like you want to predict the force field in some sort of molecule type of transformation. And the same if you do rotation also into the force field, also the force field is going to be rotated, right? So depending how you do the transformation, they are independent of each other. Or even if you want to, there's another example there, you want to identify dangerous objects, even if you are permuting the object in there, you are still obtain the same kind of list of dangerous objects. So this is a equivariance type of things. And the main limitation, it's a fact that must be defined on groups. It may not scale to real world transformations, right? Because you cannot just have all the transformation, all the list of transformations that would be possible in there. Okay, so if you go to the next slide, Johan, then you already have seen several definitions of this disentanglement representation learning. And then, well, just go very briefly. So practically, you see that we need to learn representation of the data where the individual factor of variation in the data are captured by separate distinct elements of the representation, right? So practically, we are breaking down the complex data into underlying factor in a way that each factor represents independently of each other. Right? So this is what our colleague was said. And there are some of the things why we need to do the disentanglement. Of course, we want to make the real data to be more simpler, right? So we are kind of reducing the high dimensionality of the data with underlying factors that can vary independently. Then, of course, the limitation are, can we really achieve this complete disentanglement between factors? And you saw what our colleagues presented before is not always so easy. Then, of course, the problem is how to identify these factors, right? You can do it in manual way because you know that some of these factors are clear. In some other cases, you can also discover this type of factors from the data that you have. And some other cases may not be so clear, may not be so explainable by themselves. And then, of course, the representation aims to separate these factors by making it easier for models to understand the structure of the data and how different factors contribute to it, right? And this can, as our colleague presented, can lead to more interpretive models, better generalization to new scenarios, and improved performance. Okay, so this is more than the textual part. If you go to the next slide, right here you can identify the structure of variations. So you could have transfer latent code, the list of different meaning of the variation. So you see there the observable data, you have different feature space. You can look at object size, shape, color, whatever. And you can also have going to, you have strictly, you get greater flexibility if you go on equivariant neural networks, right? And here you have representation instruction. So you have a dimension-wise versus vector-wise. You can have flat versus hierarchical topology. And you have different type of models. So here we are having latent space, so we can play around with it. Could be VIEs, GANs, diffusion models. We can have supervision, depend supervised or unsupervised, or of course we are doing some assumption on independence and causality. Okay, so the last slides in which we are really connected these two things in the mathematical sense. So here the disentanglement, you have this representation Z. Is disentanglement with respect to the decomposition in different factors, so G1 to Gn. And then there is an action, G from one domain to the other domain. And this map from the domain W to Z is equivariant between the action of W and Z, right? So here are the connections between each individual part and how we can apply this equivariant transformation so that they are independent. And then if you have this, then there is a decomposition on the Z factor such that the Zi is fixed by the action of Gz and affected only by Gi. So this is the equivariant type of information that we have. And then when we are traversing latent samples, this can be viewed as equivariant transformation operator. And this is exactly what we'll do, and this is exactly what we will go into the details. So the hope, and this is what we'll show you in some of our experiments, is this flexible disentangled representation. We are able to obtain this flexible disentangled representation that are simultaneously equivariant. And this we also show that they are not completely equivariant, but at least they are approximating to be equivariant. So Yue, maybe you can go into the details.
Okay, so thanks, Nico, for explaining the concepts. Now I will present our recent two works about equivariant and disentangled representation learning. As introduced by Nico, so the concepts of equivariance and disentanglements are actually closely related to each other, because if an object undergoes a transformation which can preserve the identity, this transformation can be called a symmetry transformation. And in our recent NeuroEPS paper, we want to unify the definitions of generalized equivariance and disentanglements under the same framework of a sequential variation autoencoders. Here is the overview of our framework. So we have the pixel space and the latent space. In the pixel space, we have different transformations we want to model. And in the latent space, we have their corresponding vector fields, W. The motion of the latent samples follows the continuity equation, or we say the Fokker-Planck equation. And we enforce the Hamilton-Jacobi equation constraint to make sure the time evolution of the posteriors follows dynamic optimal transports. And between the pixel space and the latent space, we have the encoder and the decoder mapping to make them connected. So we see our framework really allows for some new understandings of generalized equivariance and disentanglement. So here the equivariance means that at any pixel transformations can be modeled by the process of encoding, latent flow, and then decoding. Our latent flow is actually the equivariance operator. And the concept of disentanglement means that at each latent sample, the traversal directions will be the distinct tangent bundles following optimal transports. And here is the Plato notation of our generative models. So we first define a joint distribution of the input sequence X bar, the latent sample sequence, and transformation category K, and then we factorize it according to the latent sample evolution. Our model can be trained either supervised or weakly supervised, depending on the availability of the transformation category K. So if K is observed, we have an elbow which is very similar to a standard VAE. So but here we need to factorize the sequence and calculate the Carroll divergence at every time step. Otherwise, if K is not observed, we take it as a latent variable and use another posterior to infer it from the sequence. And here there's also the Carroll divergence where the prior of the transformation category is categorical distribution. Okay, so for the time evolution of the prior distributions of the latent samples, because we don't have any prior information about the input transformations, so we simply model the time evolution as a random Brownian motion. To this end, we can parameterize the prior potential as the log density of the latent sample. then according to the continuity equation, there will be a diffusion equation running in the prior evolution, and the particle is just randomly diffusing. On the other hand, for the posterior, we parameterize the posterior potential as a function using MLP, which is a function of the latent sample Z and the time step T, and then we can derive the normalizing for like density evolution of the posterior. And as discussed before, we also want to enforce the optimal transport property to the probability flow path in the latent space. And here we adopt the fluid dynamic interpretation of optimal transports. So which is to minimize the L2 Waterston distance subject to the continuity equation constraints. So here, leveraging the KKT conditions, we can derive the closed form solution, which is given by the famous Hamilton-Jacobi equation constraints. And to enforce the PT constraint, here we employ physics-informed neural network loss. So where the first term is the PT constraints calculated at every time step, and the second term is the initial condition loss, which encourages the potential to return no updates in the first step. For the evaluation of the proposed methodology, we mainly use two metrics. That's equivalence error and the log likelihood of the transformed data. So basically, the equivalence error measures how much the output transformations agree with the latent transformation, and it can be defined either in output space or in the latent space. For the data size, we adopt the 4 standard disentanglement benchmarks, including MNIST, Shapes 3D, and the high resolution ASIC 3D and Factor 3D. So on MNIST and Shapes 3D, we only consider very simple object and coloring transformations. But on ASIC 3D and Factor 3D, we consider more complex real-world transformations like robot arm movements and lighting and camera pose changes of the indoor scenes. So here is the quantitative evaluation results on the 4 data sites. So we can see our method has the best performance across the data sites and on the equivalence error and the log likelihood metrics. And here we display the qualitative results on the different data sites. So you can see our method has a preset control on the latent variables for generating a wide range of complex transformations. Another merit of our approach is that our method can generalize to out of domain data. So, for example, here in this figure, our method is trained on MNIST, but it's tested on the displays. So we can see, even though the reconstruction quality is really poor, we can see the scaling operator, the rotation operator, and the coloring operator still work well in the latent space. So one major limitation about this work is that we require the supervision or the weak supervision of the transformation sequence. But this is not likely to obtain in the real-world applications. So in our recent TPAMI submission, we target this limitation and propose an unsupervised representation learning approaches based on the sparse transformation analysis. So our paper is motivated by the ICLEAR paper of slow video analysis, which is called slow VAE. So basically, this paper shows that the temporal variations of natural videos can be characterized by a Laplace distribution. So which demonstrated that the real-world videos are usually very sparse. So here we introduce the spike and slab variable for modeling this video sparsity. So the spike and slab variable is defined as the product of the spike variable YT and the slab variable GT tails. So the spike variable follows a sequential Bernoulli distribution and it defines the transformation categories. So that means that the transformation category keeps the same most of the time, but occasionally we'll switch to another one. And the slab variable is a Bernoulli distribution centered around the one. So which will control the transformation space, like how many degrees the object will rotate in the next step. So we use the spike and slab variable to generate the data sequence for the training process. And we also infer the variable from the posterior to guide the latent sample evolution. And here is the Plato notation of the generative models. So similar to our previous work, we first factorize the joint sequence distribution based on the time evolution of the latent code ZT and also the spike and slab variable GT tails. So, and here we infer the GT from the neighboring two images. This is because the variations happening between neighboring images should contain the sufficient information about the transformation category and the speeds. And here we also propose another improvement over the previous work. So we leverage the concept of Helmholtz decomposition and to obtain more expressive latent flows. So the Helmholtz decomposition says that any vector field can be uniquely decomposed by the sum of the rotational vector field and curve-free vector field. This will increase the flexibility. In modeling very complex transformations, in particular the periodical ones like rotations. And here we display the evidence law bound of our optimization objectives. So besides the reconstruction loss, we have two curve divergence. One regularizing on the condition update of the posterior, and one regularizing the spike and slab variable. If we take a step further, we can decompose this term into the curve divergence of the sequential Bernoulli distribution and the curve divergence of the Laplace distribution. And here we show the results on MNIST. So our method can really disentangle the scaling, the rotation, and the current transformation from the raw image sequence in an unsupervised manner. And by tuning the slab variable, our method we can further have a control on the transformation space. So for example, here we can control the degrees of rotations, and here we can control the magnitude of scaling. And these are the results on the Shift 3D, where we can also achieve good disentanglement of the transformation category and space. And here we show that our method is able to traverse for more time steps. Quantitatively, our method has very competitive performance against the supervised baselines. So you can see our method is about at the same level of pole flow, which is also supervised. So because our model explicitly is trained on the composite transformation sequence, so our latent flow is very flexible in switching and combining the latent flows. So this figure shows that our method is able to switch between arbitrary transformation sequence during the traversal process. And this figure shows that our method can support linearly combining different latent flows to generate more complex transformations. In this figure, we want to show that the periodical transformations is more likely to be captured by the rotational vector fields, RZ. Here we show the results on Factor 3D and Isocer 3D. These are the two complex and real-world transformation data sets. Our method is also able to learn these very complex motions in an unsupervised manner. Okay, so that's all about the results on the standard disentanglement data sets. And beyond these results, we did some preliminary attempts in applying our method to real-world video analysis. So the first data set we tried is the Cityscape, which is an egocentric autonomous driving data set. So we downsampled the segmentation mask to the resolution of 64 by 64, and we feed the sequence to the model. These results are the identified motions. Because there's no ground truth annotation in the data set, so we can only have our interpretations. For example, we can interpret the first flow as getting closer to the front car, and the second flow as getting away from the front car. And we can also interpret the last one as turning left, because we can see the sidewalk on the right-hand side is gradually disappearing. And we further apply our method on QMS, the Q-type mice behavioral data set for social interaction modeling. So similar to the results on cityscape, our method is also able to discover some meaningful motion flows from the videos. So we can see that the latent flow one is more like the mounting behavior of the white mice, and the latent flow two is the attacking behaviors between the two mice. And the latent flow three is the investigation behavior. The good thing about this data set is that there are ground truth behavior labels annotation, so we can leverage the pre-trained behavior classifiers to tell if the samples generated by our latent flows are realistic or not. So here we adopt a pre-trained classifier and try to classify the images of our latent flows. So we can see our method gets some pretty good scores, which means that these latent flows are already well disentangled. Okay, so in the end, I want to talk about some future directions. The foremost thing is to try more advanced architectures other than VAE, like latent diffusion models or latent flow matching. These architectures are more scalable and can support high resolution images. And the second thing is to find out more useful real-world applications like video understanding or the neuroscience applications. It's also important to explore and try out other beneficial or natural inductive bias from other scientific disciplines like neuroscience or physics. And finally, it's always good to make connections to other representation learning techniques like sparse coding and independent component analysis. Okay, that's all. Thank you for your time.
Of course, if you have questions, we are more than happy to answer. I think that the main idea here is that we try to use physics-based type of implementations and try to use this one into the latent space, and we want to get more control on what we obtain in there. And
Yes.
I have to say that I get excited by all this mathematics, so I just kind of went back to kind of start doing this derivatives and so on. So this is thanks to you. So questions? Anybody? Okay, if not, maybe we can move to the next part.
Okay.
Thanks.
Okay, hello, everybody. My name is Xing Yang. I'm a PhD student at National University of Singapore. And today I will talk about the topic on disentanglement and compositionality for artificial general intelligence. And also thanks my senior colleagues, like my supervisor, Professor Jin Wang and Shui Chen again. And Actually, this topic is a little bit confusing for me because the definition of so-called artificial general intelligence is one kind of unclear even for everybody doing research. So I want to set my your expectation quite low because I'm not an expert of the AGI, but I will talk about many about how to resolve the problem of generalization with the principle of disentanglement and compositionality. And of the several years, we see tremendous improvement of artificial intelligence, very similar to those most famous movie in 16th centuries, like everybody's wanting to build some human-like robots and programs that can act or simulate what we can do. But in this talk, we want to shrink the scope we want to discuss. It's what do we define the artificial general intelligence in our scope? Maybe everybody has their own definition of this concept. Maybe it's some kind of universal superpower machine that can do and sense, can feel, can reasoning, or somebody will define it as the machine that matches us the human capabilities. And most famously is the Turing test that the tester cannot differentiate what the computer is doing or from the humans. And from their interconnections, we want to pick up a very narrow goal of our discussion. And that is, we want, at least we want the machine or the program that memorize a lot of data we fit into. And we also want the machines to generalize, even for those data that haven't seen due training, they can do new things. But the first part that everybody's doing that, everybody else is building large language model, large language model, or they doing a large scale diffusion model. They want to build up a more capable model that can memorize more data as possible. Every case is in our data life. But for academia, the other part is not that interesting. It's kind of getting boring than collecting data. And what our discussion is about the lower part, that how can we make the model generalize better with the principle of compositionality and disentanglement. And first, recap on what humans do for generalization. It's a kind of thing that we learn in some cases and apply in new unseen contexts. So consider the example I showed here that a boy wants to learn the concept of want. Maybe in his childhood, he asked his mother to sell, I want a sandwich, I want some toys. And later when he gets older, and he may get this concept of he wants some kind. For human, the generalization is closely related to the concept of compositionalities, that they can learn some kind of concept and apply to new context. So maybe I want to shrink the topic a little bit, like it's about disentanglement and compositionality for generalizations. And the talk will cover mostly about two parts. First is compositionality for artificial general intelligence. I will talk about three sub-areas. I think it's very important. First is the composition. The models, we train models that are composable to different concepts. And second is the compositional strategy, that we already have some trained models. How can we compose their expertise to do new kind of stuff? And the third thing is compositional data. That we want to build new data sets that enables us to learn more compositional skills. And the last one is that I want to investigate how current so-called general artificial intelligence models can do for compositional understanding. And I want to claim that they cannot yet reach the goal of compositional generalization yet at this time. So what we want is generalization. This can be illustrated in graphical manners as this far. When the training distribution is a subset of the full distribution, we want our model to perform good on the remaining distribution. While directly reaching this could be very challenging if we can learn the underlying low-dimensional factors. By composing these factors, we can then generalize to the entire space and even the things we cannot see. And while this conceptually works, we need to give a more formal expressions. Let's look at the generalization bound in our textbook. For example, the PAC bound tells us this equation that our training error and test errors has a little gap. The gap is bounded by the complexity of the model itself and the data set size. So it tells us 3 key points. First thing is that the more data is good. The second thing is that simpler functions prevent overfitting and gets smaller generalization error. The third one, I think the most important one, is that all the concept of machine learning depends on the assumption that the test distribution is identical to the training distribution. This is something very unlikely in real life because we cannot get all the information about the test distribution during our training. And it's prevent us to build real general intelligence. And here comes the compositionality and disentanglement that helps us. First step is that the concept of compositionality let us require less data to build the model. In our textbook, we know that we can factorize a complex distribution into some smaller factors. For example, here's 2 factors, and we can use the product to illustrate more complex distributions. And training simpler model on those smaller, simpler distributions can get use much less, exponentially less data to train more. The second one is that using the idea of disentanglement and compositionality, we can use some simpler model for each of the sub-goals and then somehow combine them. This leads to simpler model for each of the sub-goals so that it gets to less chance of overfitting in the large system. The third one, I think the most meaningful to me, is that it enables some flexible development that during the training time, we never see the cases, but the test time we can compose those smaller models to do things. For example, if we want the image capture models, we only need a detection model and some concept objects to paragraph model, and test time we can build the capture models. This is the basic idea of recent development of large language model agents. So let's boil down to some details. So the first concept I want to mention is the computational models. Is that it's models that train in a way that the big system is composed of some smaller but also capable components. We can make very simple categorization of those methods. First is the horizontal models that we want to get some parallel prediction of multiple models and aggregate their prediction to get the final answers. The second one is the vertical model that we can get some sequential predictions and get the final one. And the third one is the modular model set. In the model itself, we get some smaller components. And the first one is the horizontal composition models. And I borrowed the concept from the Hintons that they here mentioned 2 different methods of composition of distributions. First one is the product composition, that I have some simple distribution. I can use the product to illustrate a complex distribution. And most importantly, I can do this with the summation of energy functions. The second one is the mixture composition, that I can just have some simpler distribution and sum them up. And the 2 methods have their own unique properties. The first one of mixture models that they sum the probability up, so they get some smoother patterns of the distribution. And the second one of product models, they multiply the multiple densities together, and they do renormalizations. And it gets to more sharp distributions, but it's very hard to get the normalization complete. And for the first one, we have in the textbook we learned the mixture of Gaussians. Also, we have the mixture of expert, also introduced by interns. The concept is quite simple. That we have a router that select the expert according to the inputs, and the input goes through each the selected expert, and the output are weighted sum, and to get what we want. And it can represent some very complex distributions with different experts of simpler distributions. And it also gives us the flexibility of efficient training. Also, during the inference, we can arbitrarily set the number of experts we want to select. And also, the idea has been recently combined with the transformer language models that we can replace the feed-forward network with the MLE layers and introduce some sparsity or load balancing losses to help the model to learn better. And the second one I want to mention more is about the product composition of models, and it closely related to the concept of energy-based methods that trying to parameterize the distribution as energy functions. And in that term, the composition of the product of the distribution can be written in the form that we only care about the summation of the energy functions, and the normalizing constant can be rewritten as a form of those energy functions that we do not care much about. And we can build different energy-based model, like we can do some contrastive energy estimations, or recently the diffusion model is considered to be some kind of energy-based model. Or Jeff King also mentioned another idea of the product of gas expert, but I didn't see much of the work working on that direction. The first case is about the energy-based model that I can compose the energy functions arbitrarily. For example, I want two concepts to exist in one samples. I can sum their energy functions and do sampling on the new energy functions. Also, if I want to do a negotiation that I want some properties exist in the data and others does not exist, I can extract the energy functions in that way. Also, the diffusion model can be considered as a form of energy-based model that estimate the gradient of the log line. And there was a paper in ECCP 2022 that, according to different conditions, they can make different score predictions and do the summation, subtractions, and to compose samples that display some computational properties. Also, I think the classifier free guidance is an example of this computationality, because if the non-text is considered as conditions in this case, and we want the distribution to get away from the non-distributions and get more information for our desired conditions. And in the full scope, the second one is the vertical composition model. In a graphical model manners, we can consider as a graphical models that I want to get prediction of the final variables. I can go all the way through the graph through a sequence of predictions and integrate them up. But in our case, most models are doing deterministic sampling, so they just doing certain kind of sequential prediction. The first example is a very old ideas of neural modular networks. They apply it to some VQA tasks. Like they first do some task parsing, like if I want to point out where is the dog in the instance batch, it correlates to some sub probability like the localizations and the recognition, what is a dog, where is the dog, and how to describe a dog according to the layout of the images. So it has some smaller modules. First, it generates some parsing of the tasks, and then it connects different executors of the subtasks and get our final prediction. Also very popular, the text-to-image model we can consider as a vertical composable model. Like we first train a text encoder, and in the end of the day, it's even freeze in the training of the diffusion model. And we feed the output encodings to the diffusion models and do multi-step sampling, and also the predicted noise, the latent is decoded with the autoencoders. And it's the most training pipeline of training text to image or text to video or other kind of diffusion models. Also, the recent multimodal large language model nearly goes the same way, that they have trained vision encoders and certain kind of language decoders, and they project the vision embeddings to the language input and to do the inference. And those models are even freeze. So I call them computational model because they are even not trained. And this idea can be extended to broader domains. Like I have different experts to do different domain encodings and feed to a large language model to do decoding or other kind of decoders to decode to images or other kind of stuff. And we can also subdivide the model into smaller components. Like I can go through the layers in some models and switch to another model, the later layers in the another model. It's work called deep model reassembly in NIMS 2020. Instead of building those vertical or horizontal composable model, we can also build some even modular weights of the neural networks that we can train some smaller submodels using efficient tuning method like the adapters or LoRa's. And in the test time, we can dynamically replace or add or compose those experts. And this idea was quite popular this year, is that they can build a large part of adapters and doing new tasks that was never trained on. And flexibly in the downstream tasks and to build new combination that was never trained on in my training set. And computational strategy discusses another problem, that we have not the resource to train some kind of model end to end and to be composable. What I have is some kind of singular models like those large language models we have, and other kind of tools or single domain models that we can compose them into a new models that can do new tasks. And the most simple one is that we can use some prompting techniques that the input is go through iteratively through those large language models to do multiple different tasks. And similar to in last section we do the horizontal computational models. They themselves can do different tasks, and we can get different outputs and give different graphical designs of how those input outputs are organized to get the final answers. And the second one is about certain kind of neural symbolic agents. The idea is quite simple. We can execute those neural networks or those models using symbolic languages like those diagrams. And I first want to do A task and do B task and do C task. There was the planning of those different submodels. And I can obtain the final output by compose those different sequential executions of the different models. And recently, this idea has become very popular because it can be applied to the large language model very flexibly. Last year's CPR best paper goes to the visual programming. It's a case of using large language model to generate some code-like logics and ask tools or model to execute those tasks and get the final prediction. They show different tasks, but ideally this can be extended to any kind of task that can be factorized to simpler tasks. Also, this idea can be further extended to large language-based agents. The agent, the the word of agent is kind of confusing, but the idea is quite interesting. Like I can use a large language model to control different memories, the tools, the action models to do different kinds of tasks, to do the perceptions and to memorize the decision I've made and other kind of things, then compose them to do the final very complex reasoning that a singular model can never do. Also, the retrieval augmented generation can be considered as one case of computational strategy that I can use first retrieve some of the documents in the data set and using the generation language model or generator to do the generation that compose the original instruction and the document, the data I have retrieved, and to give us a full response. And the third things I will mention the computational data is that we want to collect data that can best approximate the computational nature of the model, so that we train the model on those data. It can use minimal number of data to do new tasks that without having like exponential number of data we have. So I will mention about 3 smaller ideas that can be used using this computational data. The first one is that we can just collect those computational data. So I can real world, I can collect the data with different small attribute or factors and train a model on them and build our model that can do computational risk. The second one is that, okay, I do not have such real world computational data. I can use simulations that I can control better for the different factors. Also, we can do by using some off-the-shelf data set, but augment them with some swapping the language orders or using some negative meanings to edit those original data to do new things. Very famous example is the Clever dataset that has a syntactic dataset for computational reasoning. Also, we in this series we have a paper on relation rectifications for diffusion model that will collect certain kind of augmented dataset that helps the diffusion model to do computational generalizations. Also, for the multi-model datasets, there was a good thing to do because we have like different data. For example, the text and the image dataset, they are with good pairings. I can do some augmentation on like only the text part and keep the image part identical to the original part. I can actually boost the computational reasoning because the data itself is built in the computational way. They have images and they have text. They're computational. And if I augment one modalities, I can get a more stronger models that with more rich information for computationality. Also, even if we do not have the data with some that built with computational natures, we can compose some off-the-shelf data sets to do the model training, and it's shown to have better generalization ability. There was not much paper that discussed how this would perform in computer vision, but a lot of people just defaultly mixing different data sets and do the model training. But in the language model, I find one paper that they have different combinations of data sets and do the model training. And they see that there was performance improvement when more data sets is incorporated. And they also measure the diversity, like in the data set. And they see that if the model is more diverse, we can get more higher performance for those language models. Even the total number of sample is the same as the original data sets. If the model is more diverse or capture the computational nature of the world, it gets better performance for the language model. Also, we can even we have only some limited training data sets, we can have a computational training method for those models. For example, for the ICCV 2023, we have segment anything. And the most interesting part of the paper, I think, is not the model itself. It's about how they construct the model and how the data set and how to use that data set to train models. First, because they want some kind of prompt inputs, like the points in the image, to have multiple different outputs at the same time. Because each input prompt can maybe computationally correlates to different prompts. Like I point to the handbag of the persons, it may point to the whole person or just the handbag, and they only select the output mask with minimum losses and do back propagations, and you see that it works well. The model converges. And the second one is that they construct multiple different kind of prompts for the single mask. For example, you can have a bounding box that circle out the mask, or have different points that point out the mask, and they do joint trainings and random select what kind of prompt the model should input and do the predictions. And this kind of training actually reflects certain kind of combinational natures of how we do interact. And for the last part, I want to mention something about, okay, everybody said they do general intelligent agent nowadays, but we can verify, do they really capture the computationality understanding of the world? And there was a topic on computational generalizations. It means that when we train the model to do something, maybe, for example, learn the meaning of the world, and when we reapply it to another language context, how the model will perform. Maybe the combination that the model is never trained on. And for language model, the people do not see any form of computational generalization. This 2020 papers, they evaluate some different architectures of language models on different compositional ratio for the test data, and they see a tremendous swap when the data set is largely different than the training set, but only has different composition of the word. And for the vision language model, it's the same. For a given input, we can swap the order of those words, and we can feed it to some large-scale vision language model, like the glyph, or other kind, the flamingo, or other kind of contrastive or autoregressive language, vision language model. And they say that the final performance are quite close to the renegades. So if I just swap the order of the text, and the visual language model can hardly recognize. For example, there was the case is that the grass is eating the horse, and the horse is eating the grass, and the model can very can point to the wrong prediction, even the order is wrong. And a large number of papers point out this problem. So from my point of view, how far are we from building those AGI from compositional understanding? I think if we are only training those large language models, that's not something we're very likely to be happening. Those models are mostly trained to maximize the log likelihood. They do memorization very well, but they will not do those computation really good. And the principle are quite clear. I can build some computational models using those techniques I mentioned, but there was no unified solutions that can incorporate them with the current language model training or large model training. So I think the idea of computational and disentanglement can make way sounds. We can use some computational models. We can use the strategy to build agents. We can use those build data sets that captures the computational strategies. And I think the idea of computationality and disentanglement also point out to some other directions that not fully explored. For example, everybody's building end-to-end learning models that train a model that do end-to-end reasoning. And it may point to that maybe we should resort to some non-end-to-end learning paradigms that we can build some modular models and doing the execution in the non-end-to-end procedures. Also, if I have multiple models that can do different things, this points out to the solution of distributed learning, that I can have different models doing different things, maybe can develop on different devices. And in the end of days, that's more similar to how human brain doing the reasoning thing. We do the input signal is distributed to different neurons in our brains to do the final prediction. And thank you for your listening. And our website and slides has been uploaded to this link. And also thanks everybody to participating in our today's tutorials. And also thanks to all the co-organizers and for the ones who didn't show up here. And next we have our ECCV 2022 tutorials on also on disentanglement and compositionalities, and also very happy if we can meet in the event. And thanks everybody for joining us in today's tutorial. Thank you.
Up to the slide.
Okay.
Checked and it didn't look like the slides were.
Oh, okay. We will update this up. Thank you. Oh, okay. Do we have any questions?